thank you for coming and greeting me so graciously. Today we will talk about embedded development. Not just any type of embedded development, low-level embedded development. This is typically not what you do if you work on an embedded company. It's sort of what you do if you build a real-time operating system or something like this. So there will also be some half-truths and some slideware, so don't worry, but feel free to interrupt if you have any questions. We will cover three main areas. Memory, how does it work? Entry points, where do programs start anyway? It's not as obvious as you might think. And electronics, and why would you even care about electronics? You're a C++ developer, right? But we will get to each and every one of these in time. I will need something to demonstrate on and use as like example. So we'll use this little nice Arduino here. It has a nice little SOC. SOC stands for System on a Chip, basically a CPU and some peripherals like a memory on the same chip. And it has a nice little ARM Cortex and some flash and some RAM. You can pick this up from wherever if you want to play with it and understand how it works after seeing this. So let's get started with memory. Memory, we know memory, right? In C++, this is memory. C++ point of view, it starts at 0. If you dereference it, it's going to be bad for you. And then it goes to whatever the pointer type of your program is. This is memory, right? Well, you might also recognize some of this stuff. If you are a CPU, a modern CPU, you have something called an MMU, Memory Management Unit, on board. The Memory Management Unit has this concept of segments or sections. I will be using the terms interchangeably. And you might recognize some of these names. These are typical names of segments you get when you compile something with Clang or GCC. You have the text segment, which contains your code, compiled code. You have the data segment, which contains your global variables that are mutable. Your RO data, which contains your constants, global constants. And BSS, your globals that are not initialized with any value. You have your heap and your stack, and famously the stack grows towards the heap, the other way around. So from an MMU point of view, or a CPU with an MMU, these are actually interesting. They're not just linear data. We'll get back a little bit to that. But one thing we can start by noticing here is that text data and RO data, that is actually values. So they need to be somewhere, so typically in your binary. While the other ones, they're just empty space that you need to make sure is available when your program runs. There's also something that the MMU can do. The MMU can do like virtual memory and stuff, but something else it can do is data protection or memory protection. So you can set read-only, for instance, on some of them. And if you try to write there, well, you get the famous seg fault. So this is something you can do, but you shouldn't. You can have an integer value. You can just cast it to a pointer and assign to it. And results may vary if you do this. If you do it and this integer points into the text segment, you get a seg fault. If it points into the data segment, you get very weird behavior because you probably overwrite something in your data segment. But it's allowed. It's allowed. So from the MMU point of view, we will sort of mostly leave the MMU world now, because how embedded is that? So let's look at this little guy again. We have two memories on this one, which is interesting, right? It's no longer just one linear range of memory like we had for C++. They both start their physical memory at address 0. Isn't that curious? How, when we access a variable that lives at somewhere down here in this range, how does it know which memory the variable uses or where it lives? This confounded me for a long time when I was just getting into embedded development a long time ago. So how does it work? Well, let's look again from the CPU perspective again. This might look like the C++ perspective, but it's the C++ perspective is sort of theoretical. This is the physical CPU's perspective. And the CPU also sees a long memory range that is linear. And how it works, actually, is that you take out your data sheet, and then you look at the system address map, and you go through it. And down here, there are some addresses. So this is how it looks. The two memory chips are linearized or put into sequence in the CPU's view of all the available memory. And this is not something your program does. This is something that built in to the CPU, how this works. So if you write to addresses above here, you write to RAM. If you write to addresses below here, you write to flash. ARM has done this for us. All right. So we're a little bit, but how do you, if you have a variable, how do you make sure it ends up there or there? Well, this is now the time to turn to linker scripts. And linker scripts is one of these a little bit mythical people, like it's rumored that someone knew how to write linker scripts sometime, but it's actually not complicated. So I'll just go through it. You specify a linker script with -t, and then you specify a file name. And the file name looks basically like this. It has two major sections, memory and sections. And the first part, we define memory regions. Here we have two memory regions, flash and RAM. These two are not keywords. They're just variable names. You can use whatever you want. The flash starts at 0, because that's what our data sheet said. The RAM starts at 2 million, because that's what our data sheet said. And these are the sizes of the regions. You can also put some protection here, like permissions, if your CPU has some kind of memory protection unit. All right, so that part is done. Let's look at how to get things in there. This is how you specify a section. This one is called .text. You might recognize. And what it does is basically it's a wildcard match. When you compile your program, your compiler creates a lot of symbols. They all start with something and then .text or .ro data. And this is just all of them go into the text segment, and then we pipe it to flash, which basically tells us put all of these with addresses from the flash memory. If you have another section below, it just adds on to get later and later addresses. So this is how you get the text segment into flash. Then BSS. It's almost the same thing, but now we put it into RAM, because it's nice and fast, and we don't really have any values that need to persist. So. Data. Well, data is a little bit special, because it has values that we need to persist, so something needs to be in flash. But we want the variables to sort of live in RAM, because that's where we want to edit them. So this is a little bit special. So what you do is you say that the symbols should go into RAM, but actually the values should go into flash. And we will come back to this, because it requires a little bit of finicking later. Stack is a special thing you can specify. It's not actually so special. This dot here is like a running counter of how far you've gotten in your memory. So if you have a lot of sections up here, then the RAM or the dot will sort of tell you this is how far my address counter is. And if you add to it, you will just carve out a big chunk, and then you add that to RAM. So you just have a big chunk of BS or stack here. And you might need to align it a little bit more than the other segments sometimes. All right, so with this, we can do this. We've now put the text segment in flash. By the way, that could or could not be a problem, because sometimes you can't execute from flash. So sometimes you need to put it in RAM. Sometimes you need to put certain functions in RAM because it's faster. But let's ignore that for now. Let's say we can execute from flash. We put the data here, but what is this? This is data again. That's weird. But like I said, this is where the values, the initial values of the global mutable variables live. This is where the symbols are pointing to. So we need to do something there before. We need to make sure they're in sync somehow. All right, and then we have BSS and stack. We don't have any heap here, as you can see, but that's OK. You could just add more sections and get heap if you wanted. So this is now what when we compile, this is now what the CPU sees. OK. Let's recap. Physical memory is mapped into processes, or process space, or CPU address space. You have a memory management unit on your beefy CPU. You might have a MPU, memory protection unit, on an embedded device like the ARM Cortex, or sometimes you don't have anything, and then you can just write wherever you want. Or also execute wherever you want, which is very fun. Linker scripts are used to place symbols into areas in memory, so you can control where things go. All right, moving on. Blazing speed here, because we have a lot to cover. Shell shock? No? OK. We will get back to a little bit more with the memory in this section as well, so don't worry. Entry points is where your program starts. OK, so you might think your program starts in main. That is what we tell our children. That's how programs start. This is not the truth. Instead, let's look at this typical firmware, simplified firmware. This is what's known as a super loop firmware. You have a setup function, which runs once, and then you have another function that runs over and over until the end of the power cord or something like that. Let's also assume some more things. Let's assume we're not using a bootloader or RTOS or anything. Now let's write something from scratch. We just want to put some code onto this board we have, and we want it to be executed. All right, so we have a problem here. Who calls main? First problem. Second problem, where do we go from here when we return? Not obvious. We have to go somewhere. The CPU, as long as there are clock cycles on the clock input pin to the CPU, it will not stop, ever. So what we do is we use another level of indirection, right? That's the go-to for software engineering. We create a function. I'm calling it reset handler. It's sort of a relatively common name. It's void, and it calls main, which is good. And then it just loops forever, which is just as a safeguard. Now I know this is a C++ meetup, and I know what you're thinking. Up. Let's get back to that. Hold your thoughts. Those of you who are thinking something, hold your thoughts. How do you make sure that you enter actually there and not in main or somewhere else? Well, again, a half-truth, if I may. You specify an entry point. This is how you tell your linker to build into the binary. This is where the program starts. If you do this on a C++ program that you build on like an ELF, then the loader will start here. If you don't use any linker scripts or anything, your program, if you link with libc, will start at a function called _start. And that will do some stuff, and then it will call main. If you do this, it will not start with _start. It will start with this thing. And then you have to call main yourself. So let's assume this deals with how it gets called. And we will get back to that as well. But let's assume so. This is just what we have. We have the reset handler, and we have the main function with the super loop, firmware super loop. All right. Undefined behavior. It's never nice, is it? This thing here looks innocent enough, but in C++, it's actually quite tricky. In C, this is well defined. It loops forever. In C++, it's undefined behavior. And this is a fun thing. If you ever if you type this into Godbolt or something and compile it with -02 and the latest Clang compiler, it will actually write, wait, what? Because it will optimize away the for loop. And since it's not returning, it will just keep going to the next thing it finds in the text segment, which is the, yeah. So this is slideware. Just be warned. This is also, this is probably going to be fixed in C++26, I hope, because it's ridiculous that these naive loops cannot be done like this. OK, that's a tangent. Let's leave that behind. Just be careful about that. You have to do it somewhere else. So we need to do some stuff. When the main function starts up, you have some expectations as a C++ developer that some things are in order. For one, the data values of your global data variables should have values that you specified when you wrote your program. Right now, the values are in Flash, but the symbols point to some uninitialized data in RAM. So that's not right. So we need to fix that. We also need to zero initialize the BSS segment, because you're supposed to do that. You can expect that to be done when you enter the main. So let's behave responsibly and do that. So how do we do that? Back to the linker scripts. When you define the BSS segment, let's start by clearing the BSS segment. When you define the BSS segment, you can introduce symbols that you can then use from your C++ code. So here what I'm doing is I'm using this dot thing again. And the dot is like the running counter of how far you've gotten in memory. So this is the beginning of the BSS, and then we add some stuff. And then the dot has a larger value here at the end, after it's been advanced by adding symbols. Now we have two symbols. If you do extern these in your C++ code, you will have, they will be linked in with meaningful values. So what we can do is this. C iterators. Take the first where it starts, and just plus dereference equal to 0. This is a very naive way, of course, of assigning 0 to everything between start and end, but it gets the job done. So this is how we zero initialize the BSS section. Then we need to deal with the data. And the data was a little bit tricky. Remember, there's RAM and at Flash. So the data values is in Flash. So we need actually two starting points here. We need the starting point in Flash, and we need a starting point in RAM. And the idea is, in the reset handler, we copy things from Flash into RAM so that all the initial values are available. And you can use this load adder data instead of using the dot, because the dot goes to RAM, and the load adder is sort of the start of where this at Flash goes. So that's the start of the Flash. This way, we introduce two new symbols that we can use in our program. And here again, we have the source, the Flash, we have the destination, the RAM, and we just advance the two iterators and assign from Flash to RAM. And when this is done, all the symbols, the global symbols, are pointing to valid values, initial values. All right, pretty good. Are we done? Well, not so fast. If this was a C program, we would sort of be done. But this is a C++ program that we want to write, right? So what else needs to happen?
Global constructors.
You're absolutely right. Global constructors. And how do we do that? OK. You already have this one. Congrats. Here we actually don't need to fiddle with the linker scripts. GCC or Clang or whatever helps us out here. The init array start and init array end is basically an array of function pointers that gets generated for us by the compiler. So as long as we iterate through and call every function pointer in this list, we're good. This is all that is required of us, which is very convenient, I would say. So we just need to remember to do that, and then we're good. Of course, there is also the destructors, but who cares about destructors in embedded, right? Because remember, we're not destructing anything here. We're just forever living. So let's just ignore the destructors. All right. I have something to confess. Remember the entry point? I said you could use the entry point to the linker script to get things started. Well, yeah, you sort of can. If you're writing an ELF running on Linux, or maybe in some real-time operating systems, you sort of can, because they will honor this and load it in the proper place. If we're doing some bare metal stuff, I've got news. The CPU does not care about your entry points. It has its own entry points. It will start at wherever it is programmed, hardwired to start, every time you turn the power on. So how does that look then? Well, remember this. We have something called interrupt vector table, which is a small array in the beginning. I mean, it can be wherever, but it's usually in the very beginning of Flash. And this, again, you need to look up in your data sheet for your CPU. This is hardwire, unchangeable, mostly. Let's say it. And if you look it up, you will see that at 0004 address, there must be a function pointer. Because what happens when the power comes on is that the CPU takes whatever the value is there and puts it in its instruction pointer. And the next clock that comes will start advancing the program counter from that point. So we need to put something here in the 0004. Why 0004, you ask, and why not 0? We will get back to this. So, OK. We have our reset function. The reset function needs to, the address of the reset function needs to end up here somehow. All right. But we have already covered the tools for this, right? We know how to put symbols in memory at certain locations. We've covered linker scripts. So what can we do? Well, first, we need to create the symbol. We need to create the interrupt vector table. And you can do it. This is just an array. It has a reset handler on the second place, and it actually has the stack top at the first place. So that's curious. What is that doing there? But the interesting thing now is that we're looking at where we're starting execution, right? And that is at 0004, which is the second entry in this array. Now we just need to place this array at the very first part of the flash, and then we're golden. So how do we do that? Let's first decorate it a bit. This is a way you can make sure that you get like a handle you can use in your linker scripts. So you can decorate functions. I said before that you can also put, sometimes you want the text segment in Flash, sometimes you want it in RAM. This is a tricky way you can do if you want to have a little bit of both ways. Sometimes you want a really fast function, or something weird. You want to be able to mutate the function or something. And then you can do something like that with some functions, like a RAM function, and then put the RAM functions in RAM and the other functions in text. OK, side note. By doing this, we make sure that the ISR vectors array ends up in a section called ISR vectors. Or at least that this is appended to sort of the symbol name for it. Okay. Let's see what we can do. The left side here is just the code from the last slide. And the right side here is a linker script. Now you are getting used to linker scripts, reading linker scripts here. So what we see is we put something in Flash. And if we make sure this is the very first thing in the sections, there is nothing before. Then we know the Flash starts at 0000. So this makes sure that we put the vectors tagged things in Flash. And then the other stuff comes below here, like the text segment and so on. So if we do this, actually, the C array will end up at address 0, which is pretty cool. We also needed the stack. And why is that? Well, it turns out there are two important registers. I mean, there are many important registers, but two are more important than other registers for starting. That's the instruction pointer and the stack base pointer. So we also need to make sure that the stack base pointer has some kind of reasonable value, because otherwise, like, function calling and stuff won't work. So the 0th address is actually the top of the stack. So we just reuse this. We just put in a symbol here, and we record where the top of the stack is. And then we can write it into the first address in Flash.
Why not assume that the set handler will set up the stack pointer as its first instruction?
It's just not done that way. I don't know why. Ask ARM. Maybe someone knows, but I don't know.
A lot of architectures don't do that for you, but ARM Cortex does set up the stack, and I guess you.
Maybe it's to be nice to C programmers so they don't have to do line
It's very nice. All interrupt handlers also have the same calling conventions.
Yeah. So, OK. It's just they need to do it some way. This is the way it's done for ARM. Yeah.
So if you have a bug in your program where you accidentally write to a null pointer,
Yes.
then will you update the top of the stack? And I imagine that wouldn't be a problem anymore after you've started.
I mean, after you've started, it won't be a problem. But of course, if you write to the Flash, it might be persisted. So you could be, yeah.
Imagine you would like a segfault if you try to write to a null pointer.
No, there are no segfaults if you don't have a memory protection unit,
Right.
which is the thing that segfaults you. So if you don't, this CPU comes, I think, both with and without. So you can get, I don't know for this Arduino which one it has, but
If you have writable Flash without the memory protection unit, then that's bad.
yeah.
You can really
Okay, let's explore. But this is just the way it is. Let's say the way it is, by the datasheet, by Fiat. So let's recap now what we're doing with this. We have seen the Superloop firmware, the most common type of firmware, not the only. This is what you get if you start a sketch with Arduino or something. You get this structure. We have seen that something else needs to call main, typically, to do the thing that a C programmer can expect to be happening before main is called. We've seen that there's something called an interrupt vector table that the CPU expects there to be, because otherwise it will be a very sad panda when it powers on. Or actually it doesn't care, it just runs whatever is there, which can be also interesting. Especially if you have a GPIO pin with something really expensive connected to the other end. All right, and we can use linker scripts now to place our own interrupt vector table at address 0. And there are some preliminaries we need to cover. How am I doing for time? Pretty good. Third, are you still with me? This is a lot to take in if you're not an embedded programmer already. And if you are, maybe you already know this stuff. But I hope you're not too shell-shocked. Let's move on to something really low level. I sort of teased that this is the lowest level, and this is the lowest level. Now we are leaving the realm of C++ and entering the realm of physics. It doesn't get much more low level than this. So why am I talking about this on a C++ meetup then? Well, it turns out if you work in an embedded development shop, people build hardware for you that you're supposed to program, or you get them from somewhere else. And the people that build the hardware, the circuit, do the CAD of the circuitry, they also make mistakes. Shocker. And they don't necessarily always realize they've made mistakes until you start using it. Well, they don't. If you start using it and it behaves funny, they still don't realize that they've made a mistake. You will have to sort of tell them that this behaves funny. So it's good to know in what ways electronics can behave funny, so you realize, okay, this is not actually me, this is someone else's problem. So you can communicate with your engineering friends. So let's look at some common type of things that you might find when developing C++ code that is actually not your fault. So let's start with something. Bypass capacitors. A cap is a capacitor, just short. So what is this? This is something that is used like a power bank to power or to cover for small variances in voltage that goes into the CPU, typically. It can be called a bypass cap, a filter cap, decoupling capacitor, different names. And this is two main use cases. One is to supply extra boost of power if there's a voltage drop because you turn on something somewhere else. And the other one is to reduce the RF emissions that come from a CPU is very noisy. It turns on and off and on and off. And the power circuitry can turn into RF antennas transmitting at high frequency if you don't do something about this noise. And then you take a look at this. Actually, you don't need to read this. I will guide you through it. This is just to make you feel a little bit more like an electrical engineer here. This is our Arduino SoC. And what we're looking for here are these VDD. That's the power coming into the circuit. It's coming from all directions, probably to make wiring inside easier and also spread out maybe a little bit of the power. And if you follow these, all of them have sort of a similar pattern. They all go to some kind of voltage, but there's always this capacitor that goes to ground. You can see this one, there, there, there. All of them have capacitors. And these are the decoupling capacitors. Typically 100 nanofarad for small ones that capture like high frequency noise that comes out. And if it's not very close to the physically close, it creates an antenna here. So it needs to be physically close to the chip. Some bigger ones, like this 4.7 microfarad and this one, they're like a power bank that if you have like a small voltage drop to avoid a brownout, it can sort of get some power back from this one. All right. For developers, what can go wrong with this then? Well, if you boot up and the CPU resets, if you boot the board up, and it does that not all the time, but sometimes, it can be that it's power starving, and so that it could benefit from a little bit of a bigger decoupling capacitor. If you're a hardware or like a security developer and you want to glitch the power when the boot is starting to trigger some intentional weird behavior in the CPU, like skipping over a conditional branch, then you need to desolder these first, because otherwise your power toggling in the early boot sequence won't have any effect because it will take the power from these decoupling capacitors. But then you probably already know this. So, if you are reading some kind of analog inputs in your program and you're getting frequency noise, high frequency noise, especially on the same frequency as something else you're toggling with the GPIO pin or with the clock cycle or something, this could be a problem. So you can see it on your data. Or if you start something on the same board, like a LED or something, and it resets, this can also be the same. All right. Moving on. Maybe. Let's give it some time to think. Pull-up resistors. This this is sort of a thing you maybe not learn in your CS degree, but you should. Especially if you want to read a value from an I/O pin. So if you are starting out your journey with microprocessors, you might build something like this. You have your MCU, your microcontroller unit, and you have a pin and you have a button. And you just connect. VCC or VDD is the same thing. It's positive supply voltage. You connect it with the button, and then you want to count how many times you push the button. The problem with this is when the button is closed, you have a nice signal because it's connected to the power. When it's open, it's not really connected to anything. And we say that then it's floating, and that is bad, because what you basically have then, again, is an antenna that can pick up whatever you happen to have close to it, typically your mains or something. But it also, let's dig into this a little bit more. This is how it actually looks. There's actually a pretty big resistor in here, like mega ohm big resistor, because otherwise it would be short circuit if you close the circuit, right? And what you do to fix this, or what your electrical engineer should do to fix this is bad, yeah, is this. You put a much smaller resistor here, a pull-up resistor, that is connected to power, and if it's open, well, then this is a voltage divider, and this one is very small, so it's insignificant in comparison with this one, so it's like the supply voltage. If it's closed, then you have 0 because it's direct connection to ground. So now you have two clear conditions. Okay, again, how is this your problem as a C++ developer? It seems like a glaring omission if they don't put this in here, right? Well, maybe, maybe not, because there's also this option. In your CPUs, you can have, or mostly in your SOCs, but you can have internal pull-ups that you can enable or disable. And this is a communication thing, right? Maybe your electrical engineer thought, but why didn't you use the internal pull-up? I thought, and they never put it there. So, yeah. Communication thing. It could happen to you. So how does it look then? If this happens to you, how does it look? So if you read from an I/O pin, you will get spurious reads sometimes, and it will be asymmetric. Typically, either the high or the low will be stable, but the other one will be flaky. If you, let's say we're building a counter for a button, for instance, then you will get the wrong count, and you will typically see noise like on the power grid frequencies of this. All right, I have one more. Debouncing is also a classic thing. We solve it in software because we forgot to solve it in hardware. If you have a transient input state, let's say we're measuring how many times something passes in front of a sensor, or again, we're measuring how many times someone presses a button. You have your nice pull-up resistor here, you have your button, and you have your 0, you're pulling this input, you have 0s, and then you have 1s because it's pushed, and yeah, nice. We have a nice flank here transition. We count those, and we know how many times it was pushed. Problem is, this is typically how it looks when someone pushes the button. It's not like 0 to 1, it's like 1, 0, 0, 1, because there's like, when they get close to each other, like sparks flying, and it's like physics, right? And you can put a low-pass filter with some capacitors and stuff in front of the CPU, so you don't see this so much. But you can also solve it in software, of course, typically by doing this. When you see the first one in your polling, you start a timer, and then sometime later you read it again. Is it stable now? Yes, no. 20 milliseconds is, for a physical button, is sort of imperceptible. That's the limit, sort of-ish. Of course, then you need to decide how long does this need to be. If it's too long, then you will miss double taps, and if it's too short, you will sort of not let it settle. But more than that, just make sure you talk to your electrical guy, because they or girl, because they might have intended for you to use some other internal feature in the CPU. Some of them have also internal debouncing things that you don't need to do yourself. You can sort of toggle it on and off. All right. So how does this show up for you as a programmer? If you count buttons, you get a wrong button count. Too high typically, because you get a lot of false signals. And if it's too long time, you're missing double taps. So this is sort of just collecting everything. If you want to have a Harald's photo up here, if you want to have a troubleshooting debugging summary for hardware problems that you will have to deal with sooner or later in the embedded space. Yeah, that is all. I forgot to introduce myself, by the way. I'm Anders Sundman. I work at Tobii, building eye tracking stuff. And yeah, feel free to reach out to me. And don't be a stranger. I love talking to people. Thank you.
We have time for 1 or 2 questions, but as we have also been full already. So.
Yeah. Any questions about this? Or experiences of your own? Yeah.
I have a quick question. The pointers you created in the linker script,
Yes.
are they void pointers? Because it looked like you used uint star to cast them to. My first thought is,
Yeah.
are you really lying to unsigned integers?
I've never thought about what type they are. I mean, they are like a number. And I guess you can extern them to whatever you want, but I don't think they have a type, sort of. They're just a number.
They
Yes.
don't have a type, it's just a symbol name.
Yeah.
They have to get a type if you put them in C.
Whatever.
So void pointer then?
No, I mean in C you can give them whatever. But
Okay.
from the linker script,
Okay.
Yeah.
it's be an address.
Yeah.
It's not aligned correctly. I mean the linker does not know anything about your type.
Oh.
You see the program that knows how to interpret the memory location.
All right, we have another.
Have you tried working with memory stress load to find if there is noise in the interaction problems?
How to use with what?
Memory stress loading your memory, read and writes, see the stats of that, and
Stress testing your memory, reads and writes.
Just read and write cycles. See that in action, did it see being affected by noise or something? Because
Yeah, it can be for sure. I mean, everything that goes over a bus can be affected. One of the, like, this is quite interesting actually. In a database theory, you have this CAP theorem, right? That you can use either availability, consistency, and partition tolerance, and you never get, or you always need partition tolerance outside of the embedded space. But actually, memory CPU communication is typically one of the few networks where you can allow to loosen the partition tolerance requirement, because it is supposed to be so stable that you never get any partitions, right? So if you have noise on your memory, it's not good. That it should be reliable. I mean, I'm not sure I answered your question, but maybe you can catch me later.
okay, yeah, I just want to see in practical.
Yeah.
Are there any other common patterns in embedded programming that are actually UB, except for trivial loops?
I'm sure. This is just the one that I know about, but I mean, run UB-Sun. Yeah. There's everywhere you turn. There's, especially if you do this type of pointer stuff and like the thing that Harald showed. And, yeah.
Okay, then further discussions in the break. Thanks.
Yeah. Thank you very much. Thank you.